This is part 2 of our introduction to equilibrium, and that's Untitled Chapter 15, or our Unit 7. And here's the equilibrium constant. We've already seen a hint of that when we saw the ratios of the forward and reverse rate constant. And if you've done the Show Me the Money simulation, you will see that, in fact, what we came to an equilibrium was the ratio of the forward and reverse constant. So let's look more at that. So the equilibrium constant. In the forward reaction, we go like this. In the reverse reaction, we simply go right to left, or we can turn around and show it as a forward reaction. But the rate law is this. For the forward reaction, Kf, K forward, times the N2O4, which is breaking up, and the rate law for the reverse reaction is K reverse times the square of the NO2 partial pressure or concentration. Now, what do we do with that? Well, we know the rate of forward is equal to the rate of reverse reactions, which means K forward times the N2O4 is equal to K reverse times NO2 squared. Rearranging, as we did in our first lecture, we divide both sides by Kr, and that's what gives us this. And when we do that, we also divide both sides by N2O4, which gives us this. This is the ratio, then, of forward and reverse K, which is the ratio of the products raised to their coefficient power divided by the reactants raised to its one coefficient power. Interesting. Now, the ratio of the rate constants must be a constant as long as the temperature is constant. So we simply make this happen. We divide the forward by the reverse K, and we get a big K, K equilibrium. The K of equilibrium is the ratio of the products to their coefficient power divided by the reactants, there's only one here, to its coefficient power. Therefore, to generalize, for this reaction, and you've seen it before, A moles of A react with B moles of B to form C moles of C and D moles of D. This is the equilibrium expression. Don't get confused. It's the same as we just saw, but this is more general. The equilibrium constant with concentrations, that's the little c here, would be product C to the C power times product D to the D power divided by reactant A to the A power, coefficient A, and B to the B power, coefficient B. This expression is true even if you have no idea what the elementary reaction mechanism is, because we can measure the K concentration. We can measure that all by itself, and we'll see how to do that when we do our experiment. So, I want you to just freeze the screen here, and for each one of these, write the equilibrium expression for Kc, just assuming we're doing the concentrations for all of these, even if they're gases, for the following reactions. So it'll take about 5 minutes to do that, and just turn the recorder off. Note that concentration of A can only refer to a gas or a solution, the molarity or the partial pressure. Now, equilibrium can be reached from either direction. We can start off with N2O4, or we can start off with NO2, or we can start off with a mixture. What happens? Well, let's look. If we do N2O4, nothing, and only NO2, and we get to equilibrium, here's your concentrations. Oh, so you square this, and like you have here, You square this and divide by that. I challenge you to do that. You'll come up with something close to 0.211. Starting off with no N2O4 and initial NO2 higher concentration, at equilibrium you get these numbers. So square this, divide by that, and I bet you'll come up with 0.211 or something real close to that. Same thing if you have a higher concentration of NO2 to begin with. You end up with higher concentrations of the NO2 and N2O4 at equilibrium. Divide the square of this by that, you get 0.213. And if you start off with all N2O4, you'll still come out with the square of the NO2 divided by the N2O4 is 0.213. The final ratio of NO2 squared to N2O4, that's going to be a constant as long as you don't change the temperature, no matter what initial concentrations are. So if you had some of this and some of this, you'd still end up with a 0.211. And you'll see something like that when you do our quantitative experiment. So this graph shows data from the last two trials from the table you just saw. Experiment 3 and Experiment 4. And it doesn't matter. You start off with all N2O4 or all NO2. It doesn't matter. You end up with the same equilibrium concentrations. Here's another reaction. This is a very famous reaction because it's the commercial production of ammonia from atmospheric nitrogen and hydrogen that you can just get from electrolysis, like when you're, condensing hydrogen to put in an automobile that runs on hydrogen instead of gasoline. And as you can see here, you achieve an equilibrium if you start off with no NH3 and you start off with hydrogen and nitrogen. You see you use up nitrogen, you use up hydrogen, and you produce nitrogen trihydride is ammonia. And if you start off with all ammonia, it'll break up and you'll have the same concentrations or partial pressures of all three gases at the end. This is what I call the chemical engineer's resignation letter, because instead of making ammonia, he breaks up ammonia, and that's bad. That's bad. But it's a good demonstration. It doesn't matter whether you start off with all reactants or all products or a mixture. You'll always end up with the same equilibrium unless you change the temperature. It doesn't matter. We'll have the same proportions of all three substances at equilibrium. And what's the equilibrium expression? Looking at this, the product of products raised to their coefficient power divided by the product of reactants raised to their coefficient power. It'd be cubed here and first power there. Equilibrium calculations. Let's just do some. A closed system initially containing 10 to the negative third molar hydrogen and 2 times 10 to the third molar iodine at 448 degrees Celsius can reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI, the product here, is 1.87 times 10 to the negative third. What's Kc for this reaction? In other words, you know the initial of this and this. You know the equilibrium concentration of the HI, but you've got to figure out the equilibrium concentration of hydrogen and iodine. Now, we have a special tool for that, and I'll show you that here in a minute. We need all three equilibrium concentrations, but we have only one. But we do have the initials here, and that's going to be a big help. Here's the solution, and we call them Rice tables. Now, you remember Rika tables, which you start off with a reaction, you have the initial, you have the change, and you have the after. We're going to change that to reaction, initial, change, and equilibrium. So they'll look very much like a Eureka table. So here we go. Here's the Rice method. You start off with a reaction. H2 plus I2 gives you 2HI. And the only thing you are allowed to put in here, just like in the Eureka table, you put moles or molarity. You could also put partial pressures. Well, let's just make it easy. So we know the initial of hydrogen is 10 to the negative third times 1. And of iodine is 10 to the negative third times 2. And we don't have any HI to start. At the end, we have 1.87 times 10 to the negative third equilibrium HI. Think, this is actually pretty logical. We had to add 1.87 times 10 to the negative third HI to get from 0 to 1.87 times 10 to the negative third, right? So that's the first thing you do. You work off of what you know. Now that means, looking at the stoichiometry here, that you had to lose 9.35 times 10 to the negative fourth of each of these to get twice that number, 1.87 times 10 to the negative third, change here and end up with that. So now all we need to do is subtract this minus that. Well, we'll need to change this to 10 to the negative third in order to make that happen. So when you do that, you're making this larger, so you make this smaller. So this is 1 minus 0.935, and when you change that to scientific notation, you get 6.5 times 10 to the negative fifth left over at equilibrium, and 1.065 times 10 to the negative third, because you started off with twice as much here. So you'll have that extra 1 here. All right. So we can figure out the equilibrium constant now, can't we? Because we've got all three numbers we need. There's your equation. It's this squared divided by this and this. There's your 1.87 times 10 to the negative third. We're going to square it. We then divide by this and divide by this, and the answer is 51. And you say, what's the unit? And the answer is, it's wonderful. With equilibrium constants, we don't pay attention to units. We'll explain that. Now, what does the value of K mean? If the equilibrium constant is much greater than 1, the reaction must have a lot of products because the numerator is big. So product predominates at equilibrium. If it's much less than 1, the reaction is reactant favored. The reactant predominates at equilibrium. And I'm going to stop there so that you can get the savor of this and take good notes.